Hello students, you are welcome to my YouTube channel Nepkim Guru. Hope that all of you are fine and you are watching my channel which is dedicated for chemistry. Thanks for watching my previous videos. In previous videos I have talked about different topics of chemical kinetics. Last time I have talked about the how to derive the relationship between temperature and rate constant or rate of reaction, which is called RNA's equation. If you like my videos, then you never forget to subscribe my channel and you share to your friends. If you have any confusion in the video, you comment in my videos, and uh, you share to all your friends. Okay friends, today I'm going to describe about the how to calculate energy of activation from RNA's equation. So RNA's equation can be used to calculate the energy of activation for a reaction. You have already learned about the RNA's equation in my previous video. RNA's equation can be written as rate constant K is equals to A multiplied by e power minus EA upon RT. This is RNA's equation that we have already derived in previous video. If you have not watched that video, then you can go to that video and you can watch the proof of RNA's equation. Now if you have this RNA's equation, then you can easily calculate the energy of activation from this equation. So let us see here. Now taking ln on both sides, if we take ln on both sides, so what will be the next step? Ln k is equals to ln a multiply e power minus ea by rt. This we are taking ln on both sides, so that we can separate here. Ln k is equals to ln a plus ln e power minus ea by rt. I think you know this. How do we get this? Ln a into b is equals to ln a plus ln b. So if you say this a and this small is b, then ln a plus ln b, this is ln a plus ln b. So you can write like this way, and you know this you can simplify as this equation can be further simplified in this way. Let us see here. Okay, this can be written as like ln k equals to this ln a, and this power we can keep on this side, so minus ea upon rt, and this ln e. So okay, do you know the value of ln e? The value of ln e is simply, this is 1. Ln e is equals to 1. You know ln e equals to 1, so you can put here 1. So what do you get here? Ln k equals to ln a minus ea upon rt multiplied by 1. Okay, this kind of value you can get it. So finally you can get it, ln k equals to ln a minus ea upon rt. Okay, this kind of equation you have got it, ln k equals to ln a minus e upon rt, that you can little bit rearrange here. Ln k is equals to minus ea upon r 1 upon t plus ln a, that you can just rearrange like this way. Friends, if you compare this equation with the equation of a straight line making y-intercept, this is y equals to mx plus c. If you compare with this equation, then this you can write as y, and this will be m slope, and this 1 by t will be x, and this ln a will be c. So if you compare this equation with y equals to mx plus c, then you definitely get a straight line, you definitely get a plot. So comparing this equation with y equals to mx plus c, okay, in place of y you can put there ln k, and in place of x you can put there 1 by t, and similarly c, y-intercept will be equals to ln a, and slope will be definitely equals to minus ea upon r. So friends, if you plot the graph between y and x, that is, if you plot the graph between ln k and 1 by t, what do you get here? Let's see. Okay, if you plot in y-axis ln k value, I mean ln of rate constant value, in x-axis 1 upon t value, I mean 1 upon temperature in Kelvin, then you can get a straight line passing, making the y-intercept equals to ln a, and the slope of that straight line, this tan theta, you can find out slope equals to m equals to, that will be equals to minus e upon r. Okay, so friends, if you plot the graph between ln k and 1 upon t, you can get a straight line making y-intercept ln a, which has got slope equals to m, which is equals to minus e upon r. So friends, you can easily say that ea equals to inertia of activation equals to minus slope multiplied by r. This is the graphical method to calculate inertia of activation. So friends, experimentally, if you find out a graph or plot, and if you get a straight line like this way, then if you find out this slope of the straight line, and the negative slope multiplied by universal gas constant r will be equal to energy of activation. So this is the way how do you calculate energy of activation experimentally from the graph. So friends, by using RNS equation, you can easily get the plot like this way, and you can get slope to calculate energy of activation. So friends, when you have RNS equation, then that RNS equation simply you can change into y equals to mx plus c, and you can get the plot between ln k and 1 upon t, which is a straight line with y-intercept ln a, and the slope of that straight line will be definitely equals to uh, minus e upon r, which is energy of activation equals to minus slope into r. Okay, in this way energy of activation can be calculated. Okay, from the graph we can easily say that if ln k versus 1 upon t is plotted, if ln k versus 1 upon t is plotted, then the slope m will be equals to ea upon r minus e upon r, and we can calculate energy of activation. So in this way you can easily calculate the energy of activation of a reaction experimentally or from the graph. So friends, this is the way how do you calculate the energy of activation from the graph, but we have even another way to calculate energy of activation. So the next way to calculate energy of activation is if you are provided two rate constant at two different temperatures. So what do you do? Let us see. If K1 and K2 are the rate constant at temperature T1 and T2 Kelvin. Okay, then from RNS equation you can easily write you can easily write ln K2 equals to, okay, ln K2 equals to, you can easily remember the RNS equation here. ln K2 equals to minus EA upon R, so 1 upon T2 plus ln A. Okay, this will be this can be written easily for T2 temperature. Then if we have rate constant K2, similarly for K1 rate constant at temperature T1, you can write ln K1 equals to minus EA upon R 1 upon T1 plus ln A, that you can write. Okay, these two equations are from the RNS equation, and this is for rate constant K1 and K2 at two different temperatures T1 and T2. So if equation second is subtracted from 1, if you subtract equation 2 from 1, then you can get it easily. Okay, if you subtract this equation is subtracted from 1, then you can easily write ln K2 minus ln K1 equals to minus EA upon R, that will be common, minus E upon R will be common, so that will be, okay, you can easily write minus E upon R 1 upon T2 this will be minus, and there is also minus EA upon R 1 upon T1. This will be got down, this and this will be got down when you subtract. Or this ln K2 minus ln K1 will be ln K2 upon K1. You know, ln A upon B equals to ln A minus ln B. That is the formula. So you can easily write ln K2 upon K1 equals to, this will be plus, so minus EA upon R will be common, and you know 1 upon T2, this will be plus. So and if minus EA upon R will be common, then you can write 1 upon T1. This will be the equation. Okay. So this kind of equation you can easily obtain here. Okay, or simply you can change this equation in the positive form. So or also you can write ln K2 upon K1 equals to this minus, if you open by minus, then EA upon R, then 1 upon T1 minus 1 upon T2. It will be this equation. So this is the equation, this is the final equation from which we can easily obtain energy of activation, provided the universal gas constant. So you will be provided temperature T1 and T2, and at that time you will have K2 and K1 value, two rate constant value. So if you put the K1 and K2 value and T1 and T2 value, and provided the universal gas constant R as a constant, then you can get energy of activation. So energy of activation can be calculated. So in this way energy of activation can be calculated. So friends, if you want to get energy of activation from the from theoretical concept, then you must be provided two rate constant at two different temperature, at T1 and T2, that will be K1 and K2. So in this way, by using this formula, you can easily obtain the energy of activation. This formula can be little bit changed into log. Okay, log K2 upon K1 will be equals to EA upon, this will be 2.303 R, because you know if you change ln, then it will be 2.303 into log. So E upon R, 2.303 multiplied by 1 by T1 minus 1 by T2. This will be the final formula if you use log. Otherwise you can use ln also. So friends, this is the way how do you calculate energy of activation theoretically. So RNS equation can be used to calculate energy of activation by two ways. Okay, one way is you plot the graph between ln K and 1 upon T, and you get the straight line, and then if you find the slope of that straight line, you can easily get the energy of activation value. Otherwise you can have the formula, provided two rate constant value at two different temperature, you can easily calculate energy of activation. So friends, I hope that you have understood how to calculate energy of activation from the RNS equation. So this is the way how do you derive a formula to calculate energy of activation as well. So in today's video, I'm going to even solve some numerical problems related to this calculation of energy of activation. So let us see how do we calculate energy of activation here. For example, if I take one problem that I solve here, for example, number 1, the rate of reaction doubles when the temperature, the rate of reaction doubles when the temperature is raised from 22 degrees centigrade to 32 degrees centigrade. Then calculate the energy of activation. Calculate the energy of activation. Okay, you are provided the universal gas constant R value. That R value will be equals to 8.314 joule per mole per Kelvin per degree per Kelvin, or you can write per mole per Kelvin. Okay. This is the universal gas constant R value, 8.314 joule per mole per Kelvin. Friends, this is the equation. Okay, this is the given question. How do we calculate energy of activation? Then it depends upon the unit of R. Whether R is provided in joule value or calorie. If R is provided in calorie, then you can get the energy of activation in calorie form. Otherwise, you can get in joule form. Okay, so we have provided joule value, so you can get energy of activation even in joule. So let us see here how do we solve it. Okay, now here given temperature is T1. T1 equals to 22 degrees centigrade, and that must be changed into Kelvin. That is 22 plus 273 Kelvin, and that will be equals to 295 Kelvin. Okay. Similarly, you will have T2. T2 is 32 degrees centigrade, and that will equals to 32 plus 273. That is that in Kelvin. So this is 305 Kelvin. Similarly, what is K1 value? See here, K1 value is not given there, but saying that rate of reaction is double. So this K1, if K1 is x, then K2 will be 2x. Okay, because rate of reaction is double here. Now energy of activation EA equals to what? That you can calculate. You have to calculate the energy of activation here. Now we have the formula here. We have the formula like ln K2 upon K1 equals to EA upon R 1 upon T1 minus 1 upon T2. Okay. So if you put just the value of all of the values here, then if you put R values, then K2 and K1 value, that is 2x upon x, that is ln2, it will be ln2 equals to EA upon R 1 upon T1 minus 1 upon T2. So in this way, if you calculate the energy of activation, by putting all the values of T1 and T2 and even each and everything, that you get it 51840.014 joule, small joule, that can be converted into kilojoule, that is 51.84 kilojoule. Okay, this much is energy of activation. So friends, you can use this formula and you can calculate the energy of activation if you are provided two rate constant at two different temperature. So I hope you have understood the concept here. Okay, this is the equation, this is the formula, and you can easily put the values and you can get energy of activation in joule. Friends, if you use the R value in calorie, then you can get the energy of activation value in calorie. So let us see next number. Okay, number 2. Let's see number 2. The first order rate constant of decomposition of for decomposition of N2O5 nitrogen pentoxide at 0 degree centigrade is 7.87 into 10 to the power minus 7 per minute. If energy of activation for the reaction, here given energy of activation, if energy of activation is 24,700 calorie per mole, then calculate the rate constant at 15 degrees centigrade, provided R is equals to 8.314 joule per mole per Kelvin. Okay, this is the question. Okay, this is very simple to solve because this is just like previous one. Here I think you already knew the formula. This ln K2 upon K1 equals to EA upon R 1 upon T1 minus 1 upon T2. This is the formula. Or ln this K2, you already have the calculate the rate constant at 15 degrees centigrade. So K2 is need to calculate. K2 is what that you need to calculate, and K1 is already given there, 7.87 multiplied by 10 to the power minus 7 equals to energy of activation is already given here, 24,700 calories. This is in calorie. And the value of rate universal gas constant is provided in joule, but you can use that value in you can use that value in calorie. That is this value will be 1.987 calorie per mole per Kelvin. This value is in calorie, so you can use the calorie value. Okay, you must be careful about the unit given there. So energy of activation is given there in calorie, and you have to use R value also in calorie. So 1.987 calorie per mole per Kelvin, that you can use 1 upon T1. This T1 is 0 degree centigrade, that is 273 Kelvin, minus 1 upon T2 is 15 degrees centigrade, that is 273 plus 15, that is 288 Kelvin. Okay, this you can use. And here only K2 is not given, okay, that you can find out K2. Now you find out all the values of this, let us say X. If you get X value for this all, then ln this K2 upon 7.87 into 10 to the power minus 7 equals to nt ln of x, that you can do. X means this whole value. You just find out first of all this whole value, and that will be x. Nt ln of x, that you can find out nt ln of x. If you calculate, then you can easily get the K2 value. Okay, K2 value. So this is the way how do you find out K2 value, rate constant. So if you are provided energy of activation and if you are not provided any temperature or any rate constant out of all, if one value is not given, you can use this formula very easily to solve the numerical problem. Okay, so this is the way how do you solve this numerical problem. Now friends, I'll give you here some numerical problems related to this to solve yourself. You can solve yourself. If you cannot solve this yourself, then you just comment in my videos and I'll provide you hint. So okay, let us see the question. Calculate EA, calculate energy of activation of a reaction. Calculate energy of activation for a reaction where rate at 27 degrees centigrade gets double for 10 degrees centigrade rise in temperature. Okay, and provided R is equals to 8.314 joule per mole per Kelvin. Okay, this is one of the questions that you have to solve yourself. Okay, I'll provide you next numerical problems also for practice. For a reaction, the rate constant at 550 degrees centigrade and 625 degrees centigrade are 1.1 liter per mole per second and 6.4 liter per mole per second respectively. Then calculate energy of activation. So friends, here you are provided two temperature and two rate constant. Definitely you can get energy of activation, but R value you must use yourself. So friends, today I have discussed some numerical problems as well, how to calculate energy of activation by using RNS equation. So friends, if you are watching my video, then surely I think you are getting some knowledge. You can see more and more videos in my playlist in my channel NetChem Guru. So I hope that all of you are benefited. I am going to describe many other topic, so please subscribe my channel for more and more videos. So friends, you practice from the beginning and you just don't read just before the exam, because there are lots of topic. As a good student, you must cover all the syllabus and you must know the all topic. So from the beginning, you start to read, and you can watch my videos for each and every topic of BC first year. Thank you for watching my videos. Thank you, everybody. Thank you.